One of the most common confusions that happens when we talk about maximizing an integral like this, and we'll just go back to the one variable version. One of the problems that people often have is when we start taking derivatives. So we know that to maximize that, we end up with the Euler-Lagrange equation. A lot of people get very bothered by the fact that y of x here and y dot of x are not independent. And so how can you take the derivative of f with respect to y dot while holding y the same? And how can you take the derivative of f with respect to y while holding y dot constant? And the answer to that is easier to explain with an analogy. Supposing I want to take the derivative of y of x cubed. We know how to do that. That's just the normal chain rule. We take the derivative of this with respect to y of x, and then the derivative of y of x with respect to x. But suppose we did this a different way. Okay, suppose instead we looked at the function g of a, b, and c. And g of a, b, and c is going to be a very, very boring function indeed. It's just going to be the product of a, b, and c. Now suppose we want to take the derivative of g with respect to x. Then we know from multivariable calculus that we just take the derivative of g with respect to a and a with respect to x. And we have to add, well, what if b depends on x as well? So we have this, and we also have, but of course, these two things can be made the same because y of x all cubed is just the same as g of y of x, y of x, y of x. So instead of calculating the derivative of y cubed directly, let's calculate it through g. So if we calculate the derivative of g with respect to x, then we're going to get three terms from our dependence on a, b, and c. And then if we plug in y of x into each of those, then what we're going to get is, we just plug in y of x for each of the a's, b's, and c's, and we'll get the same term each time. We'll get, which is of course exactly the same answers we had before. Now it's entirely unsurprising that we get the same answer. After all, we took the derivative of y cubed in each case. But you'll note that when we did it through g, we effectively took the derivative with respect to y, and then we did it again, and then we did it again. And that's an extreme example of what we did before. So each of those three slots had a y in it, and so it's exactly the same thing, and they were completely not independent. However, if you look at the definition of g in terms of a, b, and c, those functions a, b, and c were completely independent. Anything could have gone in there. The fact that we happen to have put exactly the same thing into a, b, and c is not g's problem. Okay, that's just part of the evaluation when we take the derivative. And in exactly the same way, if we look up at the function f, it's got a slot for y and a slot for y dot and a slot for x. And as far as the functional f is concerned, those three slots are independent, even though we then went and put two things that weren't independent in there, like the y and the y dot. In the same way that when we went to g, after we did the derivative, we went and put in y, y, and y, three things that were completely dependent on each other. So when we look at the Euler-Lagrange equation, it is indeed entirely reasonable to take the derivative of f with respect to y dot, assuming that y is independent of y dot, because the slots in f, they are independent. And similarly, we can take the derivative of f with respect to y, assuming that y dot is constant, because that, again, is a different slot.